I'm going to start with the first part. Again, all of this stuff that you're seeing here is going to be on the canvas. And so the first thing we're going to do is we're going to talk about algorithms. So everybody has some idea what an algorithm is, and we use that kind of word very easily. Like, you have a study, you got to know this algorithm, that algorithm. It's very important. What is an algorithm? Well, an algorithm, I define it in a simple way as a finite series of steps to solve a problem that always works. Finite means what? Not infinite. It means that there is an end. There is an end. It's not something that continues getting better and better and better, closer and closer and closer, indefinitely. It's something that actually comes to an end. When?
Solution.
When you arrive at a solution, and of course that means you will get a solution after you execute a certain number of steps. Now that number of steps could be very, very high. For example, something that's finite doesn't mean that you can count it on one hand. 5 is finite, but finite could be 25 trillion. Hard to count 25 trillion on your hand, but it's finite. But you can count it. 1, 2, 3, 1 trillion, 1 trillion and 1 trillion. You know what I'm saying? You can count it. It would take you a very long time. But if we are counting to 25 trillion, we can do it. It's finite. So, finite means it's part of it. Solving a problem means that we're giving steps. Steps like a recipe or steps like instructions. Do this, right? And then it always works. It means that an algorithm has to give you the proper solution every single time. Not 90% of the time, not 80% of the time, not 99.9% of the time. Always. It always gives the perfect solution by following the steps in finite time. That's it. So, we sometimes want to have a verification or a proof of correctness of an algorithm. And a proof of correctness means that we are verifying that the algorithm is actually producing the solution that we want it to produce. So we want to verify or prove the correctness of an algorithm. Let's say an algorithm's job is to sort data from least to largest. So now we want to prove that after the algorithm executes its finite number of steps, we will have that. So how do we do that? Well, we have to think about how that might be done. And why do we need to do that? Why do we need to prove correctness anyway? Well, we need to do correctness because some algorithms are very simple, but some algorithms are quite complicated. And you want to make sure that when the algorithm is actually implemented and distributed and applied to important projects, that the result of the algorithm, in fact, will be faithfully done. And the algorithm will correctly do what it's supposed to do. And if the algorithm is very complicated, and it's very difficult to even understand how it works, we may have to need a proof of it. Now, in order to prove an algorithm, we have to have some proving techniques. And, of course, it's easier to learn those techniques on a simple algorithm than on a complicated algorithm. If we have a simple algorithm and we learn how to prove it, then we'll learn the technique, and then we can apply it to more complicated instances. So, why proofs are necessary, I highlighted here basically sometimes algorithms are non-obvious. It's not quite clear that we're going to get this. Let's say we're supposed to determine an algorithm to determine let's say the nth root of unity. And we want to determine the 17th root of unity or the 22nd root of unity. Okay, first of all, we have to know what our root of unity is. And how can we prove that a root of unity is a root of unity and that our algorithm, in fact, will produce all of the roots of unity for a given value n? Okay, I just threw it out there because it's not obvious. So we may need a proof to show that it's, in fact, going to give it to us before we start implementing this algorithm and applying it to transformation series. So sometimes algorithms are not obvious, and we may need a proof to make sure that they are doing what they're supposed to be doing, so when we implement them, we can rely on them to do their thing, and do this thing correctly. Also, going through a proof sometimes allows us to view the strategy that's built in or inherent in an algorithm. Meaning that if we prove an algorithm, we may reveal how the algorithm is solving the problem. So it gives us a little bit more insight, a little bit more understanding of the algorithm. And that can be useful in two ways. It allows us to compare an algorithm with another algorithm or a set of algorithms that do similar things. They're not the same algorithms, but they sort of do their work in a similar way. So that's important for us to be able to do that. And also enables us in the future to develop better algorithms in the future times. So for example, if we have gone through the proof of 3 or 4 or 5 algorithms, and now we have to create another algorithm, we may have a better idea how to start, because we can see a class of algorithms that do similar type of work. So we may expect to be able to come up with a new algorithm that's similar to what we already have learned, and probably have it done in as many steps as the one that we already know is a very good one from this class. Okay? So that's why proofs are necessary. So before we get too much into that, let's talk about what are the techniques that we're going to be studying in this class. And there are basically 4 basic techniques. Really 3 basic techniques. These 2 are kind of the same thing. And so the first technique is a direct proof. And a direct proof is the most straightforward proof you can have. Basically, you want to prove this. P implies Q. So P implies Q. First of all, what is P? P is a statement. What is Q? Q is another statement. And what is the arrow? An arrow is called an implication. So we can read this as P implies Q, or another way of writing it, we can read it as, reading it is, if P, then Q. And what that means is, if P is true, then Q will be true. Now, since P is a statement which can be true or false, and Q is a statement which also can be true or false, you can imagine 4 possibilities. True implies true, true implies false, false implies true, false implies false, right? Now, not only does P and Q have a value of truth or false, the implication itself also has a value of true and false. So there are 3 values that we are seeing here potentially. The value of P, the value of Q, and the value of P implies Q. Okay? So that's an implication. So what we want to do is we want to prove that the implication is true. Now let me tell you when the implication is true. The implication is true whenever P is true, Q must be true. If you can show that for every P being true, Q is true, you have proved the implication. In fact, we don't care what happens to the implication if P is false. And the reason we don't care is because if P is false, then it doesn't address if P then Q. Because it's if not P. So it doesn't address if P then Q. So if P is false, we don't care about whether Q is false or true, because the implication only cares if P then Q. The implication does not care what happens to Q when P is false. The implication also doesn't care what happens to Q when, well, if P is true, then Q must be true. If P is false, then Q could be true, or Q could be false. So let's apply something real to this. So since P and Q can be statements, they can be any statements. So that means the implication, we can make an implication out of any 2 statements. If P then Q, as long as we define P and Q. Okay. So let's say P is the statement, today is Monday. Okay. And Q will be the statement, it is sunny day. So the implication is if it is Monday, then it is a sunny day. So P could be true or false, because today P is true. But tomorrow, Wednesday, Thursday, Friday, Saturday, Sunday, and then true again. Right? So P is going to be true once a week. Q is going to be true. Now, do you think the implication, if it is Monday, then it is sunny day, do you think that's a true implication?
No.
Prove it. Oh, okay. So basically, look outside. So basically say, is today Monday? Yeah, look at the calendar, it says Monday. Look outside. Is it sunny? No. Okay. So it's Monday, and it's sunny day. It's not sunny day, so therefore the implication is false. That's okay. You can have a false implication. I can make up crazy implications that are false. I can also make up implications that are true, or that might be true, or we may not know whether an implication is true or false. So if I give you an implication, I say prove it or disprove it, what do? Well, if you want to prove the implication P implies Q is true, if you want to show that it's true, you have to assume that P is true. And when you assume that P is true, lots of other things follow. For example, if it is a Monday, then you can also assume it's the first day of the work week. Why? Because Monday is the first day of the work week. Okay? If it's Monday, then somebody wrote a song called Stormy Monday about this day. Because there's a song called Stormy Monday. Anything that has to do factually from the fact that today is Monday can be used. Then you can use any of those things to show step by step and get closer to show that Q is always also going to be true. If you cannot do that, then you have not proved it to be true. But you also have not shown it to be false either. In order for it to show that it's false, you must show that here is a case where P is true and Q is false. If you can find one example where P is true and Q is false, you have disproved the implication. You have shown it to be false. That's called a counterexample. You look for something that contradicts the implication. But if I can't prove it because I'm not smart enough, or I haven't taken enough time, or I didn't concentrate enough, or I haven't worked long enough yet, failing to prove it does not disprove it. What's more difficult, to prove something to be true or to show something is false? Well, if it's true, to prove something to be true is actually harder. Because if something is true, to show that, then you have to show that whenever this is true, this must be true. So you have to show for all cases of true for P, Q must always go to false. But if an implication is false, all you need to show is one case where P is true and Q is false, and you've disproved it. So to disprove something, all you need is a counter example. And that's simple to do. You just found one example that shows you the opposite. Okay. Now, rules of inference simply means you use logical steps to go from P to Q. Okay, and we'll look at some examples. Now, the indirect proof is almost identically the same as the direct proof. We're still trying to prove that P implies Q, but rather than proving P implies Q, we prove it by proving the logical equivalent of not Q implies not P, which actually is logically exactly the same. It's also sometimes called the contrapositive. So for example, let's think about an implication that may be true. So let's say I am always happy when I have my favorite meal. Makes sense. So if I'm having my favorite meal, I'm happy. Okay? So what's my favorite meal? I don't have to tell you that, but I have a favorite meal. So if I'm having my favorite meal, I'm happy. So let's assume that that implication is true. So that means that whenever I'm having my favorite meal, I'm happy. So now, let's think about the contrapositive, which is the indirect. If I'm not happy, implies I'm not having my favorite meal. Well, if I'm having my favorite meal, I'm always happy. That's true. And here I am looking at my face and I'm not happy. Well, that implies I am not having my favorite meal. So that's not Q, implies not P. And those two are exactly the same logically. Now, are you guys familiar with truth tables? True, false. Okay. You draw a truth table of P, Q, P implies Q. It looks like this. So the truth table would look like this. So first of all, again, P and Q are going to have 4 different possibilities. That's it. So we're going to have, this is going to be P, this is going to be Q, can you see it? And this is going to be P implies Q. So we have 4 possibilities here. So we're going to have true and true, true and false, false and true, false and false. So we know the implication is true whenever P is true and Q follows it. So that's going to be true. Now if P is true and Q is false, that is contradicting the implication, so that has to be false. Now in the cases of false, true, and false, false, they are not contradicting, they are not contradicting. Just because this is false and this is true, doesn't mean that when it's true is not true. So therefore, anytime P is false, we'll just say the implication is automatically true. Why is it true? Because it's not false. It doesn't even talk about the implication. So, that's what we have here. Now, if we extend it to, for example, if we have not P, or let's say not Q, we write like this. So this is Q not. So what's the value of Q not? Well, it's opposite of this one. So this is true, this is false. This is false, this is true. True, false, false, true. And now we're going to look at not P. So not P will be the opposite of P. So it's T, T, F, F. So it's going to be F, F, T, T. And now we're going to look at the last one, which is going to be not Q implies not P. So if you look at this one, false implies false, it's true. False implies true, also true. True implies false is false, and true implies true is true. So if you look at these values, TT, FF, TT, TT. So notice that this truth table is exactly the same as that truth table. So that logically shows that the indirect proof is an equivalent proof to a direct proof. Except, now why would you want to use the indirect proof? Well, you'll see an example why it may be easier, more useful to do that. What do I do? All right, so make sense so far? Okay, now be very careful about the implication. If the implication is if I have my favorite meal, means I'm happy, or implies that I'm happy. If you see that I'm happy, what does that imply? It implies nothing. And the reason it implies nothing is because it's not that every time I'm happy, I'm eating a meal. It's just when I'm eating my favorite meal, I'm happy. So that causes this P causes this Q. But it doesn't say only and only when I'm eating my favorite meal am I happy. That's different. That will be an if and only if. I am happy if and only if I'm having my favorite meal. But that's not what I said. I said if I'm having my favorite meal, I'm happy. Also, Also, if it's a weekend, I'm happy, because I like weekends. So if it's Saturday, since that's a weekend, right, I'm happy. If it's Sunday, I'm happy. So now you don't know whether I'm happy because I've had my favorite meal, or it's Sunday or Saturday, or both of those things are true. Also, when it's payday, I'm happy. Right? Also, when I teach 502, I'm happy. So lots of things could cause happiness, but happiness does not cause those things. So make sure you understand that the reason that arrow is moving from P to Q is a reason for it. Okay. So now, the inductive proof is another kind of proof. It's a very powerful proof for interesting algorithms. And the inductive proof, basically, you want to show that a particular statement is true for all possible values, say, of an algorithm. Let's say the algorithm is going to operate on data of size 1, 2, 3, 4, 5, 6, or any integer greater than 1 or equal to 1. And you want to make sure that the statement, which is the algorithm, is true for all of them. So therefore, you want to show that the algorithm is correct for all positive input values. So the smallest positive input value would be 1 if you're using positive values. So therefore, you would have to show that P of 1 is true. And that's usually pretty easy to do. You plug in 1 into the statement, and you see if it's true. If it's true, then you say it's true. Of course, you're trying to show that P is true for any n, which is a positive integer. So that's an infinite number of cases, but you're showing that the basis, the first one, is true. So now what you do is you make an assumption that P is true for all values j, where j is greater than 1, because you already proved that one, and less than some hypothetically large value n. So you're making an assumption that the statement is true for j in this range of values, from 2 to n minus 1. And after you make that assumption, you show that using the assumption that P of n must be true, when our value exceeds j by 1, it will still be true. And so that's called an inductive proof, and it's a proof by induction. And we will use the proof by induction, but I will also prove that induction is a valid proving technique, because it sounds like a little bit like hocus pocus, a little bit like magic. But in reality, it's actually a valid proving technique. I'll prove that induction is true. The proof by induction is actually a proof. Because people can tell you, okay, you just do this, but it's like, really? Okay, you assume something and then you show that one more, yeah? Another way sometimes people are taught to do this is they show that P of 1 is true. Then they assume that P of k must be true for any value k, which is greater than 1. And then all you need to do is show that it's still true for P of k plus 1. So that's another way of doing it. It's the same thing. You're just trying to extend the assumption by 1. Here, our assumption of j in this range ends with j being n minus 1. And then we show that one more is still true. When we assume that P of k is true for any k, then k plus 1 is one more than k. Same idea. Okay, and the last proving technique is also a very powerful technique. It's called proof by contradiction. So what you're trying to do is you're trying to show that something is true. You're trying to show P is true. So I make a statement, and that statement I said, prove that P is true, do it by contradiction. Now let's suppose P is a statement which actually is true. Always. So what we're going to do to prove by contradiction is we're going to make an assumption that in fact P is false. And if P is false, as we are assuming, that lots of things fall or follow from P being false. When P is false, then lots of logical things follow from that. For example, if I say somebody who is 6 feet tall or taller, blah, 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 the negation is somebody who is not 6 foot tall or taller. That means that what flows is that they are 5'11" or shorter. You follow what I'm saying? So logical things are things that you can deduct or deduce from something being true or something being false. For example, if I say the passing grade for this class is 70, and I say Scott did not pass the class, we can deduce that his grade was less than 70. And your name is? Leonita. Yeah. If I say Leonita passed the class, sorry, then we can deduce that his grade was 70 or higher, right?
And what is the difference between indirect proof and proof by contradiction?
So I didn't finish this one yet. So it's a proof by contradiction. We're trying to prove something to be true, so we do exactly the opposite, assume it's false, and then we take all the logical things that follow from falseness. Then we use those logical things to show that all the things that are following from P being false actually lead to a contradiction. Something that cannot be true. So if the assumption of falseness leads to a contradiction, the assumption of falseness is false, and P in fact is true. Get the idea? That's kind of how it works. Okay. All right. Oh, I didn't know it was almost 8:30. Look at that. Wow, time for breakfast, right? Okay, so let's take a look at some examples of these. And you're going to see that they're not that tough. You just have to pay attention, figure out how it works. It makes a lot of sense. So let's do an example of the most straightforward one, which is going to be a direct proof. So we're going to use a direct proof. And direct proof, we're asked to prove directly that if n is an odd integer, then n squared is an odd integer. Now, the first thing I would do is I would take an odd integer. Oh, I don't know, like 1. I square it. Is it still odd? How about 3? I square it.
Yes.
How about 5?
Yes.
7?
Yes.
9?
Yes.
11?
Yes.
13? How about 1,235?
Yes.
Okay.
Yes.
So you might not be so sure. How about, right? So you might not be so sure about that one. How about 1,000,000,001? Square, quickly. No. So we might not be sure. So what we want to do is we want to prove. It seems to us that in the examples we tried, 1, 3, 5, 7, 9, 11, we did not find a contradiction. If we did find a contradiction, then we can say this is false. Because if n is odd, I found an n squared that wasn't odd. All you got to do is find 1, and that disproves everything. So it is not enough to try 1, 3, 5, 7, 9, 11, and say, okay, proven. Put it into a space shuttle. And all of a sudden you get a number and it comes out even, and the shuttle has a disastrous flight. Oh, we didn't prove it. We thought going up to 11 was good enough. Sorry. Can't have that, right? So we need a proving technique. So we're going to say if n is odd, then n squared is odd. Now what is an odd integer? An odd integer, we can say, is an even integer plus 1. Every odd integer is an even integer plus 1. So what is an even integer? Well, an even integer basically is 2 times an integer. So for example, 2 times 0 is 2 times 1? 2. 2 times 2? 4. Times 3 is 6, times 5 is 10. Times negative 1? Okay, so basically if I have an integer in the form of 2 times k, where k is an element of the integers. You know this one? K is an element, z is a set of integers. When k, so for any k element of the integers, 2k is an even integer, right? And we can produce every single even integer if we put in an appropriate number for k. So we're going to assume that n is an odd integer, and an odd integer basically is the general even integer plus 1. Hey, what about minus 1? Minus 1, that's okay too. Which one's better? It doesn't matter. Your choice. So what we're going to say is if n is odd, then n must be equal to 2k plus 1 for some integer k. So therefore, n squared of this general odd integer will be 2k plus 1 times itself, which comes out to 4k squared plus 4k plus 1. Now what we want to do is we want to show that this is also odd, and plus 1, we love that, so we keep it out here, and then we see what we can do is we take out 2 out of here, and we have 2 times 2k squared plus 2k, which is what? Even plus 1, and we see that 2 times this is an even, therefore 2 times this plus 1 must be an odd. Easy, right? That's a direct proof. So again, if n is odd, then we use the facts that follow from it being odd. And that is going to be the fact that if n is odd, then it's an even plus 1. And then we use those facts to build and see if we can get it to look like an odd after we square it. Now, let's take a look at the following next proof. So this is going to be a proof we can do directly or indirectly. If 3n plus 2 is odd, then n is odd by indirect proof. Now the problem with 3n plus 2 is odd, it's a weird way to put it. So this is p, and this is q. But actually, since this is p implies q, we can also say this is the same thing as not q implies not p. And that way we can have, if n is not odd, then 3n plus 2 is not odd. But we know if an integer is not odd, it's even. So therefore we can rewrite this by saying, therefore if n is even, then 3n plus 2
Is it not odd? Not
is
odd.
even. Is not odd, is even.
Is even.
Okay, so here's what we have. So the contrapositive or the indirect proof basically is going to say if n is not odd even, then 3n plus 2 is not odd, also even. So therefore n becomes the general even number, which is 2 times k for any integer k. And then we have 3 times n plus 2 becomes 3 times the 2k, substitution, plus 2, which gives us 6k plus 2. And what we want to show you is that the 2 can be factored out across the whole number. And so we take the 2 out, and it's 3k plus 1. And so we know that 3k plus 1 is an integer, and 2 times an integer is an even integer. Proof is done. So we proved not q implies not p, which is equivalent to p implies q. Okay? Any questions on that? All right, now we also have a possibility in some cases that we have two statements, P and Q, and we have what we call a biconditional. And a biconditional is basically, notice that the arrow is going from P to Q, but it's also going from Q to P. What that means is that what we're saying is that P implies Q and Q implies P. That's different than before. Now we're saying not only do you go forward, you can go backward. And whenever you have this condition, you can write it with a single double-headed arrow, and we read it as P if and only if Q. Because it means that P is true, Q follows. If Q is true, P follows. So they are implying each other. They're implying each other. So we read it as if and only if. So can you think of something that's an if and only if? Can you think of a P and Q, not from my example, but anything else? Let's do something very simple. If an angle is acute, then it's less than 90 degrees. If an angle is less than 90 degrees, It's a good. Could it be obtuse? No. Okay, so you understand. So it's not super, super hard, but it's a very strong relationship. I have an angle that's acute. Okay, it's less than 90. I have an angle that's less than 90. Okay, it's acute. You understand. So it's a biconditional. One implies the other. So let's say we want to have a proof given a triangle with sides A, B, and C. We want to prove A squared plus B squared equals C squared if and only if the triangle is a right triangle. So we're saying A squared plus B squared equals C squared. If that's true, the triangle is a right triangle. And if the right triangle is a right triangle of size ABC, then this is equal to C squared. You understand what I'm saying? Okay. So in order to prove a biconditional, you really need to prove this direction. You need to show that this implies this, and that this implies that. So a biconditional proof is basically two direct proofs, because you got to go each direction. So don't be too happy after you finish the first direction, because you got to go the other way to show the biconditional. So now we're going to say if the triangle is a right triangle, so this is the proof now. If the triangle is a right triangle, then the Pythagorean theorem can be used to show that A squared plus B squared equals C squared. So we're proving it by saying, well, Pythagoras already proves it, so we're going to, he said basically if it's a right triangle, then this is true. Now, we also have, do you remember in the triangle we have the law of cosines? Remember that law of cosines? Comme ci, comme ça. That's okay, don't worry about it. But the law of cosines basically says that C squared equals A squared plus B squared minus 2 times AB times cosine of an angle which faces this one. So for example, just to remind you very quickly, so if we had a triangle here, so we have here, this is A, this is B, this is C. Well, actually, these are going to be so this is going to be A, this is going to be B, this is going to be C. We can call this, for example, alpha, we're going to beta, and maybe gamma, or something like this, or whatever, right? So what we're saying here is that C squared is equal to A squared plus B. This is for any triangle, is the law of cosines, minus 2 times this side, AB times the cosine of the angle that faces C. So in this case, it's going to be cosine of gamma. And by the way, B squared is equal to A squared plus C squared minus 2AC times the cosine of what faces B, which is going to be cosine of beta. And by the way, A squared, you understand, right? So now, so what we're going to do here is we're going to say the law of cosines is a law. So in a triangle, the law of cosines can be used to show that in the equation here, the only way that we're going to get A squared plus B squared equals C squared is if all of this is 0, right? 2 is not 0. Why? Because it's 2. A is not 0. Why? Because it's a triangle. B, not 0 because it's a triangle. So therefore the cosine of the angle must be equal to 0. So the cosine of the angle must be equal to 0. So what is the cosine inverse? Cosine inverse of 0? 90. You understand cosine inverse of 0? So cosine inverse of 0 is 90. So that means that C must be 90. And therefore this must be a right triangle, because a right triangle is a 90-degree angle. Make sense? Yes? No? Maybe?
Yes.
Good. All right, so these are examples of the biconditional. So when we get together on Wednesday, we're going to start cranking away at this stuff. We're going to start doing induction. We're going to be doing contradiction. We're going to show induction. We're going to show a bunch of different examples. So right now, just enjoy, relax, wait for Canvas to tell you. The notes are in. And so you will always have all the notes in the class. I still recommend that you take some notes that will help you remember what I'm talking about and focus on the important parts. Then you can resolve them with the notes if you need to. Okay? See you on Wednesday.